Lighthouse Scientific Education presents a lecture in the Acids and Bases series. The topic, Acids and Bases, Advanced Concepts. Material in this lecture relies on an understanding of the previous lectures, Acids and Bases, Basics, pH and Titration, and Stoichiometry, Problem Solving. This lecture expands on topics covered in the previous acid and base lectures. Not all students will need to be proficient in all of these subjects. Check and verify what is expected of you. The lecture begins with a review of the dissociation of water and rolls into the dissociation of various acids and bases. There's an introduction of the acid-base dissociation constants Ka and Kb, and a discussion of how their conversion into pKa and pKb is used to indicate the strength of an acid and base. And then it is on the practice of converting between the concentration of hydrogen ion and pH, and vice versa. Finally, a look at using stoichiometry to solve an unknown concentration using the values of a titration experiment. The dissociation of water serves as a foundation for the dissociation of acids and bases. Autoionization, self-ionization, or autodissociation are terms that represent the breakdown of a compound into ions. While an infrequent occurrence, a molecule of water, H2O, will break down into hydrogen ion and a hydroxide ion. As seen in the pH and titration lecture, in pure water, a hydrogen ion is the same thing as a proton and is also a hydronium ion. They are, for the most part, interchangeable, and that is how they will be treated in this lecture. For pure water at 25 degrees Celsius, the concentration of hydronium ion times the concentration of hydroxide equals 1.0 times 10 to the negative 14th. That is a constant value and given the designation Kw. Kw is the water ionization constant. Also from the previous lecture, we saw that Kw can be expressed as pKw by taking the negative log of that 1.0 times 10 to the negative 14. The P stands for power of, and any value can be made into a P term by taking the negative log of its value. The negative log of 1.0 times 10 to the negative 14 is 14. A P term has the single purpose of converting small numbers into the more comfortable range of counting numbers. That is all that it does. Dissociation of acid or base in water can be viewed the same way. An aqueous acid, shown here as the generic HA, will sometimes dissociate into hydrogen ion, hydronium ion, and a conjugate base, A-. That is the formation of an electrolyte. Importantly, the reaction goes in both directions. That's what the double arrows tell us. H plus and A- combine and reform the acid HA. That is even true for strong acids like hydrochloric acid. Most of the time, this acid is treated like it completely dissociates. But a tiny fraction of the time, the acid is reformed. It is the general rule in chemistry that all reactions go in both directions. For weak acids and bases, this happens to a significant degree. If our generic acid is allowed to come to equilibrium, that is when the forward reaction is occurring at the same rate as the reverse reaction, then the concentrations of the acid and the ions will remain constant. It is not that the acid has stopped dissociating. It is that an equal amount of acid is reforming. An analogy would be a fountain pouring water into a pool. The volume of the pool stays constant because an equal amount of water is being drained away and sent back to the fountain. The concentration of a compound, amount per volume, can remain constant even though there is a continuous breaking down and reforming of that compound. Under equilibrium conditions, the ratio of the concentration of products over the concentration of the reactant is a constant. For an acid, that constant is called Ka, the acid dissociation constant. this type of ratio is similar to the product of hydronium and hydroxide concentration found with the auto-dissociation of water. It too has a constant, Kw. Ka and Kw are based on the ratio of concentrations at equilibrium. Equilibrium is an advanced subject, but all we need to know here is that it is the condition where the concentration of compounds in a reaction remain constant. Like for HCl. In water, at equilibrium, the ratio of concentrations comes to a value of 1.3 times 10 to the positive 6. That number is only completely true for a specific temperature, so Ka's come with the temperature. Usually a Ka is given at 25 degrees Celsius. Since this Ka is larger than 1, a lot larger, the numerator is larger than the denominator. Multiplying the concentration of the products together is a larger value than the concentration of the acid. That makes sense when we consider that HCl is a strong acid and will almost completely dissociate into ions. For weak acids, the Ka will be less than 1. The concentration of the acid in the denominator will be much larger than the ions in the numerator. The Ka lets us know which acids are strong, Ka larger than 1, and which are weak, Ka less than 1. That is roughly true. There is a better way to handle Ka. With the Kw of the auto-dissociation of water, a pKw was made by taking the negative log of the Kw. Same thing can be done with Ka. pKa is the negative log of the Ka. The purpose of pKa is the same as that for pKw and pH. Make very small and very large numbers easier to handle. pKa is a way to see how strong an acid is at a glance. Acids with a larger pKa, that is a smaller Ka, favor association or the reforming of the acid. These are weak acids. Remember that negative sign is there to make the negative exponent in the scientific notation into a positive number. Very small numbers have large negative exponents and will therefore have large pKa's or pH's or whatever P is being calculated. When one direction of the reaction is much more favorable than the other, the reaction arrows indicate this with disproportionate size. With a glance, the preference for associated or dissociated acid can be seen. Acids with a smaller pKa, that's a larger Ka, favor dissociation or ionization. The reaction arrows for such acids would show a favoring of the formation of ions. The same argument can be made with an aqueous generic base. It is in equilibrium with its hydroxide ion and conjugate acid, B+. Like the weak base, ammonia, there's a water molecule involved in this reaction that is not shown. That is where the hydroxide and the acidic hydrogen in the ammonium ion comes from. The water is implied with the aqueous subscript. Like the acid, we can take the concentration of the components of the dissociation of the generic base at equilibrium and place the concentration of the products over the concentration of the reactants and get a constant. For bases, it is Kb, the base dissociation constant. It only holds when the concentrations are at equilibrium. For the weak base, ammonia, the ratio of concentrations comes to 1.8 times 10 to the negative 5. That holds when the solution is at 25 degrees Celsius. This Kb is a very small number, which means that the value in the denominator, the base, is much greater than the concentration of the ions in the numerator. That strictly comes out of an understanding of how fractions work. The reaction arrows favor reformation of the base. As with Ka, Kw, and the concentration of hydrogen ion, Kb can be converted into pKb through the negative log. For bases with larger pKbs, that's when Kb is small, like with ammonia, the reaction favors association, reformation of the base. The larger reaction arrow is towards the reactant. For bases with smaller pKbs, that's when Kb is larger, the reaction favors dissociation, formation of ions. The larger reaction arrow is pointed towards the products. Generally, students at this level of chemistry will only need a basic understanding of how pKa or pKb can give the strength of an acid or base. That is, given these generic reactions and a table of acids or bases with dissociation constants, the student should be able to recognize relative strengths of the acids and bases. For example, which is the weaker acid, the 1.85 pKa sulfurous acid or the 7.5 pKa hypochlorous acid? It takes a bit of study to get these straight. The negative log of the power, P, switches around larger and smaller. Earlier, we saw that the larger pKa's favor association. They favor more acid at equilibrium. More of the reactant acid means less of the dissociated ions, less hydrogen ion. Larger pKa's are weaker acids. Strength is about dissociation. So, the larger 7.5 pKa belongs to the weaker acid. Again, the student just has to straighten out the direction of strength in their mind. Though there is a handy shortcut for acid strength. It is to ask if the pKa's were pHs, which one would be more acidic? A pH of 1.85 would be more acidic than a pH of 7.5. So a 1.85 pKa acid would be more acidic than a 7.5 pKa acid. More acidic acid, stronger acid. There is one more component to a fuller understanding of Ka and Kb. Not all students are asked to have this level of understanding. It starts by bringing back the base reaction of ammonia in water and its calculation of Kb. In this reaction, the ammonium ion, NH4+, is the conjugate acid of the base ammonia. As such, an acid reaction can be written with ammonium ion that has ammonia as the conjugate base. This reaction has its own Ka. All we've done is write the reaction in both directions. Now, consider what would happen if we multiplied Ka and Kb together. 5.6 times 10 to the minus 10 times 1.8 times 10 to the minus 5 is our old friend 1.0 times 10 to the minus 14. It is the same value as the water dissociation constant, Kw. Does this make sense? Well, if instead of multiplying the numerical values of Ka and Kb together, we multiply the concentrations of the compounds in the two reactions, this isn't going to be as bad as it looks, because there's a fair amount of canceling going on. The ammonia in the numerator of one fraction cancels with the ammonia in the denominator of the other fraction, as does the ammonium ion. What's left is the hydrogen ion times the hydroxide ion, and that is our definition of Kw. When a reaction is written in both the acidic and basic directions, their Ka and Kb multiply to Kw. This is only for acid-base reactions in water. Without going into the math, Ka times Kb equaling Kw can be written as pKa plus pKb equals pKw, or 14. Again, this holds only for Ka and Kb of the same reaction written in both directions. What this equation allows for is that pKa of the acid reaction to be calculated from a known Kb and the number 14 from pKw. It also allows the pKb of the base reaction to be calculated from a known pKa and 14. This is advanced stuff, and not everyone will need to be able to employ it, but there will always be an instructor or two out there that feels that this is important material. If that is not your instructor, then do not spend more time with the material than is needed. Another topic that spans a range of expectations is the conversion from pH to hydrogen ion concentration and vice versa. Some students do a lot of this and some do none. While pH is the most common form of power calculations, all power calculations are done the same way. That includes wanting a pH from the negative log of a given hydrogen ion concentration, pOH from a given hydroxide concentration, the pKw from the Kw, a pKa from a Ka, or a pKb from a Kb. These are all negative log calculations. The other type of conversion is getting the hydrogen ion concentration from a pH using 10 raised to the power of the negative pH, or the hydroxide ion concentration from 10 to the negative pOH, or Kw from pKw, Ka from pKa, Kb from pKb. These are really just two types of conversions, and we'll look at both types from the perspective of the calculator. Since not all calculators are the same, we will look at two different kinds of calculators that take different approaches. First, to getting the power values from concentrations or constant values. For example, what is the pH of a hydrogen ion concentration of 2.5 times 10 to the negative 6? This calculation is a negative log of the concentration. Many students bring a hand calculator to chemistry class. Pictured here is a TI-83. To determine pH, or P anything, remember they are all the same calculation, begin by striking the plus minus key. That will take care of the negative. Do not use the minus key. Sign changes use the plus minus key. Sometimes it is just labeled as the minus key. Then strike the log key. For most calculators, that is a labeled key. For some, it is a second function key. Figure out which one it is on yours. Before entering the concentration, begin a set of parentheses. The concentration is given in scientific notation, and that is how it should be entered into the calculator. Start with the coefficient of the scientific notation. Here it is 2.5. The tricky part is the 10 to the minus 6. Avoid using a multiplication sign here. 2.5 times 10 to the minus 6 is one number, and the calculator has a way to input the exponent part of the scientific notation. On this calculator, it is a second function EE button. That is 2 keystrokes. The EE button is there specifically for scientific notation. It literally means 10 to the, and only needs negative 6 to complete the number. Again, plus minus sign is used to change sign, close parenthesis, and hit equal or enter. 5.6 should come up. A word or two about EE. For some calculators, it is a second function button. For some, it is not. For some, it is given as small ee or exp. This button simply has to be learned on your particular calculator. And then there are the parentheses. For some calculators, they are required. In some, they are not. Every calculator has to be learned, usually through trial and error. The other type of calculator of interest is one found on the computer or phone. Here's a very common calculator, and a good one to practice on. To get that same pH of 5.6 from this calculator, begin with the concentration value and punch in the coefficient, 2.5. Its 10 to the button is labeled exp. To input the exponent, negative 6, strike the plus minus button and the number 6. With the concentration in the calculator, ask it to take the log by striking the log button. The last thing to do is take care of that negative sign. That is done by multiplying the log by -1. So strike the multiplication key, the plus minus, and the number 1. Hit equal, and get the 5.6 value. The calculators actually give a much longer number, but the final answer is rounded to 2 sig figs, like the 2.5. A comparison of keystrokes for the two calculators show that they approach the calculation from the opposite direction. One is almost a direct input, and the other does so in reverse. The conversion out of pH looks more complicated, but is actually easier. For instance, given a pH of 8.6, what is the hydrogen ion concentration? The equation for this calculation is 10 to the negative pH, or 10 to the negative 8.6. Starting with the hand calculator. The most difficult part of this calculation is the 10. It can be directly typed into the calculator, but that misses the strength of modern calculators. These guys have a button for 10 raised to some power. Often is the same key as the log key, but as a second function. If that is so, there will be a 10 raised to the x power written in small yellow font, just below or just above the key. To use this second function requires the second function key to be struck before striking the log key. With this done, the negative 8.6 is added, beginning with the parentheses, the plus minus, and then the number 8.6. Close parentheses, and strike equal or enter. 2.5 times 10 to the negative 9th. Some calculators do not require parentheses for this calculation. Now to the computer calculator. Most of these have a 10 raised to the power x button, so all that is needed is to input the exponent and press that button. 8.6, change to negative sign, strike the 10 raised to x button, and equal if necessary. And again, comparing the two calculators shows them to approach the calculation from the opposite side of 10 to the minus 8.6. Practice these and do the calculations the same way every time. The last topic of the lecture is looking for a specific type of calculation associated with titration. We will look at the form of titration, that is the method for determining the unknown concentration of an acid or base. It exploits a neutralization reaction in which an acid and a base combine to form salt and water. Water is neutral. As shown in the pH and titration lecture, titration is a process that takes the solution of a known concentration, the titrant, and slowly adds it to a known volume of another solution of unknown concentration, the titrate. Addition of the titrant is continued until the reaction reaches neutralization. In the previous lecture, the unknown concentration of the titrate was determined using the equation molarity of the titrant times the volume of the titrant is equal to the molarity of the titrate times the volume of the titrate. The unknown in the equation, the molarity of the titrate, can be solved for generating this equation. If the titrate is the base and the titrant is an acid, the equation looks like this. If the titrate is an acid and the titrant is a base, the equation looks like this. While these are very useful equations for getting the molarity of the titrate, they are limited in their application. They only work when the acid and base are in a 1-to-1 ratio. That is, in the balanced chemical equation, for every acidic hydrogen, there's an available hydroxide base. That, however, is not always the case. When it is not, we fall back to solving the unknown concentration using stoichiometry. This lecture is not focused on developing the practice of stoichiometry. There's a whole series of lectures on that topic. Rather, it uses stoichiometry as a way of understanding and solving for the unknown concentration in a titration experiment. A brief review of the 5-step procedure for solving stoichiometry problems, as shown in the stoichiometry problem-solving lecture, will be given prior to their employment in a titration problem. Step 1. Write out and balance the chemical equation of the reaction of the problem. For titration, this will be a neutralization reaction. Step 2. Use the basic problem-solving technique of searching the problem for known and unknowns. Identify the given or current substance, the titrant, and the wanted or desired substance, the titrate. Step 3 is to write out the mole ratio, coefficients, and substances from the balanced chemical equation, and to put this ratio in the center of the solution equation. The orientation of the mole ratio in a titration problem will have the moles of titrate over moles of titrant. Step 4 is the get into moles part of the stoichiometric solution. Convert given or current units, molarity of titrant, into moles of the given or current substance. The conversion factor is placed in front of the mole ratio in the solution equation. The moles of titrate will need to be converted into the unit type asked for in the problem. This will generally be molarity. Place this conversion after the mole ratio in the solution equation. The first 3 steps are the mole ratio steps. Step 4 is getting into moles, and step 5 is getting out of moles. Time for an application of the rules in a titration problem. Titration found that 14.5 ml of 2.5 molar sulfuric acid was required to neutralize 25.0 ml of a sodium hydroxide solution. From what the problem has told us so far, can we identify which compound is the titrant and which is the titrate? Well, the titrant is a known concentration and has a known volume added to the titrate, which has a known volume but an unknown concentration. Since the sulfuric acid is given a concentration, molarity, it must be the titrant. That means that the titrate is NaOH. What is the molarity of the NaOH? Step 1 in solving this titration problem using stoichiometry is getting a balanced chemical equation. Is this equation balanced? There is 1 sodium on the reactant side, but 2 on the product side, so no, it is not. Notice that on the reactant side, there are 2 acidic hydrogens, but only 1 hydroxide. If they were in a 1-to-1 ratio, we could have used the equations mentioned earlier to solve the problem. Since they are not, we will have to proceed down the stoichiometric path. Adding in the correct coefficients has the equation balanced. For step 2, find the known and unknowns in the problem. The problem gives values for both the volume and concentration of sulfuric acid. The volume is 14.5 ml, and the concentration is 2.5 molar. Sulfuric acid is the current substance. Since molarity is defined as moles per liter, we will save ourselves some work by converting that 14.5 ml into equivalent amount of liters, 0.145 liters. What else can be gleaned from the problem? There is a volume given for the titrate, NaOH. Known is 25.0 ml of sodium hydroxide. Again, for convenience, ml is converted into liters. 25.0 ml is 0.025 liters. We do not have to do this now, but stoichiometric equations are busy enough without adding metric conversions. What is not known is the molarity of the sodium hydroxide. With this step completed, it's time to find a mole ratio. But since this is a titration problem, we can ask, what are the moles of the titrate? What are the moles of the titrant? The titrate is NaOH. There are 2 moles of those. The titrant is H2SO4. There is only 1 mole of those. The mole ratio is 2 moles of NaOH over 1 mole of H2SO4. Insert the mole ratio into the middle of the solution equation. Step 4 is getting into moles. Get the volume of the acid into moles of the acid. What converts volume of a concentration into moles of that substance? In the stoichiometry problem-solving lecture, we developed a graphical representation for getting into moles, mole ratio, getting out of moles. When getting into moles from volume, use the molarity oriented with liters in the denominator. Insert the 2.5 moles of sulfuric acid per liter, such that liters cancel out. This orientation also allows for moles of sulfuric acid to cancel out, leaving moles of sodium hydroxide. But moles are not asked for. Molarity is. What converts moles of a substance into the concentration of molarity? Returning to the graphical representation and looking at the get out of mole side, molarity is obtained when moles are divided by volume. Multiplying by 1 over volume is the same thing. Insert that after the mole ratio, 1 over the volume of sodium hydroxide, 0.025 liters. The remaining units in the solution equation are moles over liters, molarity. Getting out the calculator gets 2.90 molar NaOH. This is a standard stoichiometry problem. While we have the calculation still up, let's compare this to the equation used for a similar problem in the previous lecture. It is an almost identical calculation. Molarity of the acid times the volume of the acid divided by the volume of the base gives the molarity of the base. What differs in the two calculations is the mole ratio. If the acid-base mole ratio is 1 mole over 1 mole, then the math is exactly the same. If not, then the mole ratio is needed, and stoichiometry is the way to solve for the unknown concentration. And that completes the material of the lecture. As a recap, water is capable of autoionization. In pure water, at 25 degrees C, the hydronium concentration times the hydroxide concentration comes to a constant value of 1.0 times 10 to the minus 14. And that's Kw. Dissociation of an acid or base can be viewed the same way. In water, the generic acid HA can break down into hydrogen ion and the conjugate base A-. In water, the generic base BOH can break down into hydroxide ion and the conjugate acid B+. Ka is the acid dissociation constant. For the generic acid at equilibrium, it is the concentration of the products over the concentration of the acid. Similar to how the hydrogen ion concentration was converted to pH, the Ka can be converted to pKa. It is simply a way to make the very small Ka of most weak acids easier to handle. A larger pKa, which corresponds to a smaller Ka, favors association. There is more acid than ions. A smaller pKa, which corresponds to a larger Ka, favors dissociation. There are more ions than acid. Kb is the base dissociation constant. For the generic base at equilibrium, it is the concentration of the products over the concentration of the reactant. A pKb is generated the same way as a pKa. A larger pKb, which corresponds to a smaller Kb, favors association. There is more of the base than the ions. A smaller pKb, which corresponds to a larger Kb, favors dissociation. There are more of the ions than the base. A single acid-base reaction can be written as the weak acid forming its conjugate base, or the reaction can be flipped and written as the weak base forming the conjugate acid. With the same reaction written in different directions, Ka times Kb is equal to Kw. This equation can be converted into the relationship pKa plus pKb equals pKw, which is 14. So if the pKa is known, the pKb can be solved for, and vice versa. All power values, be they pH, pOH, pKa, or pKb, can be converted into their non-power values by the same calculation. Using the equation for the conversion into pH from a known hydrogen ion concentration, we outline the keystrokes for the conversion using a hand calculator and a computer-based calculator. Using the conversion into hydrogen ion concentration from a known pH, we outline the keystrokes for the conversion using a hand and a computer-based calculator. The last topic of the lecture was titration. The previous lecture solved some titration problems with these equations. In this lecture, we used stoichiometry. We got into moles of the titrant using its experimentally determined volume value and its known concentration. A mole ratio was gotten from the balanced chemical equation. It will take the form moles of titrate over moles of titrant. The unknown concentration of the titrate was obtained by dividing by the known volume of the titrate. And that concludes our lecture. Understanding acids and bases is understanding concentration and volume.